Hello, welcome to College Algebra, section 5.1. My name is Rob Reynolds. Today we're going to be looking at polynomial functions. Basically, what is a polynomial function, and then how does it behave around the roots, whether it passes, bounces, or I'm going to call this the twist and shout if it's an x cubed or x to the odd. Okay, so a little bit about the calendar again. We're starting chapter 5 today. We're going to continue this week through 5.4. We'll do 5.6 next week. Keep in mind the chapter test is Thursday. No school on July 4th, but your test will be due on Thursday. You've got your My Math Lab test that'll be released maybe even as early as Monday, so look for that. All right, so what are polynomials? Polynomials are anything with an integer, a positive integer for a degree. So x to the third is a cubic, degree 3. X to the 7th, we'll say it's a 7th degree. Those are good polynomials. Sometimes we call this the quadratic, but it's a degree 2. This is a cubic, but wait a minute. This is no longer a polynomial because they just took the square root of x. The definition of a polynomial is you can't take the square root of x, you can't divide by x, you can't raise x to the 1/2, which by the way is the same thing as taking the square root of it. You can't take x to the negative first, which is the same thing as dividing by x. You can't do anything to x except raise it to a positive exponent, like 3, 7, 2, 4. So if anything is happening to x other than being raised to the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th degree, then it's not a polynomial. Sometimes it's easier to talk about what you cannot do. So again, you can't raise it to a fractional exponent, no negative exponents, can't take the absolute value of it, and you can't even take the sign of it. No longer a polynomial. You can't do anything to x except raise it to a positive integer. No fractions, no decimals. It's got to be smooth and continuous. Those are two key words, smooth and continuous. Some of you are going to be graphing today. And you're going to look at things that look like this, and that's not a polynomial if it keeps coming up to a nice point. It's got to be smooth and no holes and no asymptotes. No removables is the holes. So looking at this, is this a polynomial? Yep, it's raising to the 4th power. This is not a polynomial because you're dividing by x. This is not a polynomial because you can't take the square root. This is a good polynomial. It's a linear function at 0. This is a good polynomial, and this is a good polynomial. Again, I'm not doing any of the things that I shouldn't be doing, like raising it to the 1/2, which is the same thing as the square root, or dividing by. Not taking the absolute value and not taking any trig functions or any logs. So nothing can happen. So again, anything in the form of y is equal to x to the 2nd or y is equal to x to the 3rd, and then you can decrease this. X squared plus 5x plus 2, doesn't matter. Now, you can even say plus 2/3, so you can have a fraction there. You could say plus the square root of 7, still a polynomial, plus 8 to the negative 2nd. This is still a polynomial. So just because you see a square root doesn't mean that you can't take the square root of a variable. You can take the square root of a number or raise a number to the negative exponent. You can even say plus sine of 53 degrees. This is still a polynomial. Again, what the difference was is these are all numbers that I was doing all this bad stuff to. Even the 2/3 dividing by 3. You just can't divide by x, take the square root of x, raise x to the negative 2nd, or take the sine of x, but you can of numbers. So again, smooth and continuous. This is what it should look like. This is what it should not look like. Can't have any sharp corners or a cusp called here. No gaps, no holes in the function. It's got to be continuous and smooth for a polynomial, looking at the graph. So this is to the 1st degree because it's 3x to the 1st. This is to the 2nd degree, 3rd degree, and a 4th degree polynomial. Be careful on your x squareds. The y equals x squared is the blue function. Notice that y equals x squared is actually between 0 and 1. It's a lower function. Those values are less than y. Let's just call this this blue function the y equals x to the 4th. I'll just come up with an exponent. So normally when I go over 1 up 1, it doesn't matter if it's 1 squared or 1 to the 4th. That's a point that they both functions share. But I wanted to highlight between 0 and 1. On the x squared function, it's above between 0 and 1, but then it's below. All of these points are below my x to the 4th. But in between 0 and 1, it flip-flops. Same thing for x to the 4th and x to the 8th. X to the 8th will always be larger than x to the 4th, except for those values between 0 and 1. And then which function is greater and which function is less flip-flops between 0 and 1. So you can graph it on your calculator, but it's very hard to see what's happening here between 0 and 1. So that's why I'm trying to highlight that for you. There should be symmetry with respect to the y-axis, and these are for x to the even functions. So x squared, x to the 4th, x to the 8th. They all kind of look like u's, or they might look like a double u, or they might have even more humps in there. This last one that I just drew cannot be an x squared. It can't even be an x to the 4th. The minimum that this could be is an x to the 6th, because it's always one less turn. So 1, 2, 3, 4. It has 5 turns. So the minimum that this could be is x to the 6th. If this has 1, 2, 3 turns, the minimum this could be is an x to the 4th. And since this has 1 turn, the minimum that could be is an x squared. But keep in mind, this could also be an x to the 4th, or x to the 6th, or x to the 8th. It's just this guy here cannot be an x squared because of the number of terms. But it could be x to the 6th. We don't know. All right, so we've been talking about odd functions. They're going to be your s's. Same thing, between 0 and 1, watch out for that property. Between which function is greater and which function is less. It changes between that 0 and 1 because of those fractional exponents. So basically, what did you learn? If it's even, it has symmetry about the y-axis. Be careful. If it's odd, it does not have symmetry about the x. It has symmetry about the origin. If you were listening to some of the earlier videos, I've got my 3-O rule. It has an odd function, has symmetry about the origin, and the third O stands for opposite. If you replace x with negative x, you get the opposite of the function. So I just wanted to highlight some things that are happening. It looks like several of the points are the same between even and odd. So several things are the same, but several things are different. So watch out for these rules. So we're going to look at transformations. When I talk about transformations, I'm talking about your h's and your k's. X minus h, your h is your horizontal. If it says plus h, it moves to the left. If it says minus h, it moves to the right. If it says plus k, it moves up. If it says minus k, it's going to move down. And then your a is called your vertical stretch. Instead of over 1, up 1, it always goes over 1 and then up whatever the value of a is. Now, if a is negative, it will go down. So I'm going to rewrite this one in this general form. This could be an x to the 5th or x to the n. We could call it x to the 6th, but in this case, it's a phi. Now I'm going to rewrite it. Negative 1, x minus 0 to the 5th plus 1. So I can really clearly see all of the values. Y is equal to a, x minus h to the 5th, which just means it's going to be an S shape. So my ending behaviors are going to be the 1st and the 3rd, because, oh, no, it's not. Because of this negative, it's going to flip-flop. So instead of 1st and 3rd, I'm going to go 2nd and 4th are my ending behaviors. So I know the graph ends way over here and way over here. Again, because it's negative, x to the odd, it's in the 2nd and the 5th. And it looks like it's shoved up 1 unit, but it's not moving left or right. So it's my S shape, because I know y equals x squared look like the parabola. Y equals x cubed looks like my S shapes. Y equals x to the 4th could be a U, but most of the time it's kind of this W. And then it just keeps alternating. X to the 5th would be in this 1st and 3rd, but it might have an extra little bump going on. But the ending behaviors are still 1st and 3rd. In this case, it's negative. So again, 2nd and 4th, we're going to flip that S around. It's an S shape. Don't move left and right, but move it up 1 unit. So instead of being 0, 0, it's up here. And then it's over 1, up A. But in this case, since A is negative, I'm going to go over 1, down 1 to find the other point. And it's symmetrical on the other side. If you want to find more points for this, to graph this more accurately, you're welcome to plug in for X's and Y's, but this will do fine on your test. Just make sure that I can tell that you have your starting point at 0, 1, and you're going over 1, whatever the value of a is, in this case down 1 from that start value. The book goes ahead and shows you how to do it in stages, but they have the same final answer that we did. So again, this is going to be an x to the 4th. I know my ending behaviors are going to be positive and positive because the value of a is positive. It's going to be going up. If the value of a was negative, it would not be a w, it would be the letter m. So this is an x to the 4th, where this would be a negative x to the 4th facing down. Looks like it's got a horizontal shift of 1 unit, and it's actually going 1 unit to the right, because when you set this equal to 0, we get x equals 1. So instead of it being at the origin, it's shoved 1 unit to the right. That's the root. In fact, we've got all 4 roots at the same spot. So all 4 roots are going to be right here at 1, 0, but instead of going over 1 up 1, we're only going to go over 1 up a half. That's because the value of a is a half. That's going to make it fatter. So I kind of like that. Fractions make it fat, and then numbers make it more narrow. So we can kind of remember a trick here that the f's go together and then the n's. So what do I mean by more narrow? Well, instead of y equals x squared, just the regular graph, if we do y equals x to the 4th, it's much more narrow because it's going up 2 to the 4th is 8, where 2 squared is only 4. So the height, it's more narrow. Where fractions make it a little bit wider, depending on which fraction it is. So my ending behaviors are still the same, but instead of going up as sharp as I was before, it's going up a little bit less. So it makes it a little bit fatter. So again, here's your final solutions. Again, the goal here is to be able to graph these without a graphing calculator. So try to, as you're doing your assignments, try to think about how to do your assignments without a calculator. So we're going to talk about multiplicities here. Where are the roots, and what happens if you have a double root or a triple root? So in this case, all of these are called roots. It's just this is a double root here because it's bouncing, and then all these other ones are just passing. So if it's a single root, if it's to the 1st power, then it's called a single root, and we're just going to pass through it. But if it's a double root, we are going to, I'm going to call it a bounce. I think my math lab calls it, what do they call it? Something besides bounce, but you'll figure that out. Touch. I think they call it, it touches the axis. I don't like the word touch. Bounce is a little bit more descriptive of what's happening there. So if 3 is a root, then what the heck is the factor? It's going to be x minus 3. So let me give you a little definition here. If the factor, I'll write it this way, the factor is always equal to x minus the root. So if I give you a factor of, if I give you a root of -3, which means that the function crosses at -3, then the factor is going to equal x minus a negative, which I write as x plus 3. So remember, whenever you see parentheses, you just go the opposite direction, because when you set it equal to 0, you have to subtract off. So that brings us to, well, okay, if I give you 3 roots, how do you find the polynomial? Well, you got to multiply, stack, and add. Remember, x minus 4 gives me x plus 4 as a factor. The -2 gives me an x plus 2, and the +3 will give me the x plus 3. So I'm going to go ahead and FOIL these first 2 terms together. The outer is 2x, the inner is 4x, for a total of 6x plus 8. And I call this multiplying, stacking, and adding. So here we go. We're going to multiply this all out to get x cubed plus 6x squared plus 8x. I'm going to continue multiplying. I'm going to distribute the -3 throughout. -3 to every term. And here's where I'm going to stack. So -3 times this x squared is -3x squared, and I'm stacking it on top of my other x squared terms. -3 times 6 is -18x, and I don't have a term to stack -24, so I'll just create a new column for that. So I call it multiply. I've done that. I've stacked like terms, and now the last step is to simply add. So here we go. Adding this up, I get x cubed plus 3x squared minus 10x minus 24. And if you were to graph this on your graphing calculator, hopefully it will have roots at -4, -2, and 3. In fact, I could even look at what this looks like. There's -2 is a root, -4 is a root, and 1, 2, 3 is a root. Since it's a x cubed function, I know that the ending behavior is first and third, and they're all single roots. They're all to the first power, so I know they're just going to pass, pass, pass. So pass, pass, pass. I don't even know what the y-intercept is. I could find it, but actually I do know what the y-intercept is right here, -24. So this is a great, I know that the y-intercept should have been negative, and there's that point, 0, -24, and it's verifying my calculator. I could verify this on the calculator, but I don't think I need to because that -24 is helping me right out. Oh, it looks like I did verify it. The only thing I haven't talked to you about is that value of a. And we need to write that value of a because it could be a 3 or a 4, and what that does is all my roots are the same. All three of these graphs are correct. It's just that a equals a negative, then instead of in the first and third, it's going to be in the second and the fourth. So they stick this a here because, well, it says find a polynomial with degree 3, but it doesn't know, we don't know the exact equation because we don't know what a is. So we'll just stick a in as a variable because it could be a determining factor. So for this, it says list all the zeros and their multiplicities. I might even ask you to graph the thing, but the multiplicities is the number of times that each factor is being multiplied by itself. So the first root that we see is 2, because when I set this equal to 0, I get a 2. Then the next root is a -1, and the last root is a 3. But the question is, what's the multiplicity? Well, the multiplicity says how many times do I see this as a factor, and this multiplicity is just 1. But this multiplicity is a 3 because it's being raised to the third power. And this multiplicity, it's being raised to the, so a multiplicity is just saying what's the exponent on that. It's how many times that factor is being multiplied. So, and then the graph is going to behave differently depending on its multiplicity. So it says find the x and y intercepts, and then use those to graph the curve. So it looks like we've got an x-intercept of 0, but it's bouncing at 0 because the multiplicity is a 2, so it's not going to pass, but it is going to pass through at the other root. So the factor is x minus 2, so the root is a 2. And if I were to multiply this together, it'd be a y equals x cubed function. Since it's positive, it's in the first and the third. So I'm going to bounce here at 0 because it's a double root, but I'm going to pass, that's not what it's going to do. It's going to pass here, but bounce at that 0. So there it is. I'm going to pass through here, bounce at 0, and that matches my first and third. Oh, the book is going to say go plug and chug some points. I'm not a big fan of that, so that's not what I'm looking for. But they end up with the same kind of graph that I do. So we're going to continue looking at, oh, this is just talking about that bouncing, haha, like the basketball is my x squareds, and then I use this scenario of this little girl passing. If it's raised to the first, it's like passing the football. You're just going to pass through. So there's the pass in red, and then this purple is coming up and it's actually bouncing off. So know the difference between bouncing and passing. So a pass would just be like a linear line, where the bounce is forming the parabola. So I've got a double root here at 0, and I've got a single root at 1. And that's what this is talking about. This x squared is in green, that's bouncing, where this is just to the first power, so it's just passing through. And then this is talking about the number of turning points. Remember, it's always 1 less. So since this is a 1, 2 turns, this equation's got to be at least an x to the third. It cannot be an x to the first, but it could be greater. Again, remember how to find your minimums by guessing left, guessing right, guessing on, but we're not going to use our calculators for these sections. So remember, not a polynomial. If it has a hole, this is a polynomial. This is not a polynomial because it has this sharp edge or cusp, and this is a polynomial. So yes, so these on the right are polynomials, the ones on the left are not. So polynomials look like this. Ending behaviors, you should know this is going to be an x to the even. It might be squared, it might be to the 4th, 6th, or 8th. This has got to be x to the odd. It's got to be, and the odd's got to be 3 or greater. It can't, well, it could be a line, I suppose. That's still ending behavior, so we'll say x to the odd. This has got to be what? Y equals x to the negative even. Could be like negative x squared, negative x to the 4th, negative x to the, and this is y equals x to the negative odd. So make sure you know your ending behaviors. So which one of these is x? All I have to do is look at x to the fourth and say, oh, my ending behavior. So it can't be this one because the ending behaviors are not in the first and the second. Oh, the other nice hint is the y-intercept is -6. So this one's out because that looks like the y-intercept is a positive. So I know that this is either -6 or this is -6. I've got, oh, this one cannot be x to the fourth. I've got too many terms. So let's see, 1, 2, 3, 4. I got 5. So at minimum, this has got to be an x to the sixth. So, and I've only been working with an x to the fourth. So I would choose letter B for that function without a graphing calculator. That's a great multiple choice question. And I did that through the process of elimination. So remember, if a function is bouncing, it's going to come down here and have a double root. And it's just, that doesn't look very good. I don't know where the double root is at, but perhaps it's at 2 and it's going to bounce. If it's a single root, it might just pass through. And then I haven't talked about a triple root, but we know that x cubed functions do this twisting, and I have a little YouTube clip that I show my class of chubby checkers singing twist and shout. So we'll twist and shout through x cubes, x to the fifths, x to the seventh, x to the eighth. So these ending behaviors we're going to talk about as well. If it's not in factored form, the first thing you might want to do is factor this thing. So if I pull out an x and look for factors of 12 that differ by 1, I'll come up with 4 and 3. Hopefully signs are going to be different. The larger term is positive, so x plus and x minus. So my roots are at, don't forget about this one. This one says the root is at 0. Ooh, I can't get to my graph very well here. I'm going to move this graph up. There we go. So there's a root at 0, there's another root at -4, and then the last root is at 3. And they're all single roots. It's an x cubed, so I know the ending behavior is first and third. And I'm simply going to pass through all 3 roots because they are all single roots. Now, don't worry about how high or how low. Your graph might look a little different than mine. Maybe your graph looks like this, and that's fine. I don't really care on this test. I don't care about maxes and mins. I'm just looking at end behaviors and the roots. We'll worry about how high or how low. Again, the book's suggesting, well, if you really want to find out how high or how low, you can just plug in random points. But I'm not a big plug in for x and solve for y kind of guy. I'm just looking for general shapes of these things. So for this one, I want you to notice you have a double root at 0, a single root at 4, and a single root at -1. If you were to multiply this together, it would be an x to the fourth function, because x squared times x is x to the fourth, which means my ending behaviors are first and second. So these ending behaviors are really important to grab. And I know I'm going to be bouncing at 0. So I'm going to pass through this bounce and then pass. And I get that nice W shape where everyone hopefully can see that I'm bouncing at that 0 because that was that x squared term, and I'm passing at the other functions. Again, here's the actual graph of the thing if you want to plug in some points. So practicing again, this would be a bounce at 2, a pass at -2, and a pass at 4. So this time, if I multiply it together again, it's an x to the fourth, but the bounce is over on this side. And these are passes. So this time, the bounce is here at my 2 because this is the factor that's called the double root, and that's why it's bouncing there. Oh, this is a good one because this is the first time that you're seeing a triple root at 4. So I'm going to twist at 4 and I'm going to bounce at -2. Let's see, if I multiply this together, it's an x to the fifth. So I know my ending behaviors are first and third, but I'm going to twist. And I want you to twist the heck out of this thing. Don't be shy. Even though the graph of it might look like this, be very convincing on your test. Twist and a bounce. Ugh, I kind of missed my bounce. So twist and bounce, boom. And just be convincing, because some of your twists on your test might look like passes, but you have to be very convincing that it actually is a twist. This is interesting. We got a bounce, a pass, and this is not a bounce, although some of you might think it's a bounce. The root for this last one, so this root's at 0, this root's at 2, but to find the root, remember we set it equal to 0. So this root is actually an imaginary root, and because you can't take the square root of a negative. So what do imaginary roots look like? Well, they sometimes cause the function to squiggle, because if I were to multiply this together, it could be x squared let's see, that's next to the fifth. So the end of behaviors are first and third, just like my x cubes. But at this 2, I'm going to pass, because this is a single root. So I'm going to pass here, and I'm going to bounce here. But because there's an imaginary root, I'm not exactly sure. There might be something else down here. There might not be something here. Or there might have been something over on this side. But you can't squiggle over here and squiggle over here, because then it's got to be at minimum an x to the 7th. So either I would do nothing, or I would have one squiggle. So let's see, 1 turn, 2 turns, 3 turns, 4 turns. My guess is it squiggles, but I'm not going to sit here and pull out a graphing calculator. You can look at it. It might do this. That's what imaginary roots do somewhere. But it might be down here and squiggling. It might be squiggling in here. I doubt it. Or it might be squiggling up here. That's not going to do both, because that would create too many turns. Oh, I had my class create one, make one up. And then this was reminding you how to guess left, guess right, guess on. Multiplicity, multiple choice, and this is another multiple choice. I hope that was helpful for you. Email me with your questions.